Hello everyone and welcome to my video tutorial on Introduction to Graph Theory using Python and NetworkX. This is the first class of a series, Introduction to Network and Graph Theory. My name is Innocent Okuluku. Objectives of the class today: to present various examples of networks and graphs, to present reasons why network and graph theory is important to study, to discuss the basic concepts of network and graph theory, to set up a computer to enable the use of NetworkX in Python, to write and run some basic NetworkX Python programs, to draw and analyze simple graphs and networks. Motivation: a good knowledge of network and graph theory is a very useful tool for future computer scientists and also in many other professions. Because of the wide range of applications of network and graph theory, from the sciences and engineering to the social sciences and arts. The topic will also increase the knowledge of the students or the participants in Python programming. Learning outcomes. At the end of this class, participants should be able to describe different types of networks, list some reasons to study network and graph theory, define a network or graph and some basic terminologies in graph theory, describe a digraph and weighted graph, identify and differentiate between graphs and digraphs, create graphs from various issues, substances, relationship, etc., draw graphs and digraphs by hand, install NetworkX and required libraries in Visual Studio Code, write and run Python programs for creating and drawing graphs using NetworkX. Content: Introduction to Network and Graph Theory. Examples of networks. Why study network and graph theory? Network / graph, digraph and weighted graph. Definitions: Introduction to NetworkX, installing NetworkX in Visual Studio Code, creating graphs in NetworkX, and then we'll have a lab for network and graph theory. So we'll see some examples of networks and we'll look at session networks, which have become very popular nowadays. We'll look at communication networks, information networks, computer networks, transportation networks, biological networks, all of which are based on graph theoretic concepts. The first example we are looking at is social networks. In the diagram we see below, which is from the book of Filippo Mensah, you can see this graph that consists of the dots, blue dots, which are called nodes. So this is a visualization of a network of Facebook users at Northwestern University, and these dots, which are the nodes, actually represent people, while the blue lines that are connecting them, very dense, they are called links or edges. They represent friend connections. So the principles of graph theory or network theory that we are going to learn in this course is going to help us to be able to understand, draw the graph, and analyze the relationships in this kind of networks. Communication network. The diagram you see here is also from the book of Filippo Mensah. It's a visualization of the defunct Enron Energy Company email communication dataset. So the nodes represent people, while the links represent email communications. So we're actually using networks here because the relationship between graph theory and network science is that graph theory actually holds the mathematical foundation of nodes and connections, whereas network theory is actually when you move beyond the mathematical foundations to the application areas. So anything that has nodes and links connecting them is a graph. So when it becomes big and it can be described by many other different parameters, it becomes a network. So sometimes the word graph and network are used interchangeably. However, if you read many of the modern books in network science, you are not going to see a lot of the mathematical theoretical foundations of graph theory, which is actually the basis by which the networks were created. So that is why it is good for us to be able to learn graph theory as a course first of all, and have a firm mathematical grounding on the theories and the ideas before we eventually move to the application areas, which is network science. The next example we see is information network. The World Wide Web is the largest information network, and below is a visualization of Wikipedia information network related to the subject of mathematics. This diagram is also from the book of Filippo Mengsa. So here we are. The big white node in the center is subject mathematics itself on Wikipedia. And then all the other nodes you see here that are drawn in different colors represent various sub-subject areas of mathematics. I'm not sure all of them are captured here because I know some areas of mathematics that are not captured in this diagram, but nevertheless, let's see how much we can see from this diagram. So on the top here we have this purple node, set of nodes, which is very dense, that has to do with historical Greek mathematicians. So I'll use the word mathematicians for the purpose of space. Historical Arab mathematicians, the subject of mathematics and art, contemporary Indian mathematicians, the red side here, historical Indian mathematicians, the subject of game theory, the subject of statistics, mathematical software, pedagogical theory. Like I said before, this is from the book of Filippo Mengsa. Alright, so when we look at this, you already know that only a very tiny subset of the areas of mathematics have been captured in this picture, but you can see how the nodes connected is very, very dense. These are the kind of things we can do with graph theory that we are going to learn in this course. We can perform analysis, we can do research, and we can produce outputs. Another example is computer networks, the internet. So the internet is the largest network of computers, devices. It's a network of networks. So we see a visualization here. This is a sample of a computer network. What you see on the left hand side is a server, which is usually a big connector that has a router by which other workstations or all other computers in the organization can connect to the server computer. So what you see on the right hand side shows a portion of the internet router network. The colors are routers representing the geographic distribution of the networks. So you can see all this blue, the light blue on the top right hand side is one geographic location of routers. The green one on this side is another geographic distribution of routers, so on and so forth. You can see the dense connectivity, and this again is from the book of Filippo Mengsa. I guess by looking at this page, we can already see the difference between the World Wide Web and the internet. While the World Wide Web deals with the information that is on the internet actually deals with the hardware that stores the information. Okay, so we are not done with computer network yet. We also talk about network of vehicles. These are mobile networks. These are actually computers. All these vehicles you are seeing here, the drones you are seeing here, about 1,000 of them or more, they form a computer network, a mobile network. It's just like the same computers that are in your office connected by a router. All of these mobile computers can also be connected to a server via a wireless router. In this case, the connection is through the air, Wi-Fi or something else. So this is the first example of vehicle computer networks. Then we also look at transportation networks. If you go to openflights.org, you are going to see a diagram like this that is showing you the current flight path of what is going on in the airspace in the world at that moment. The nodes you see here, which are the dots, actually represent cities, and the links you see connecting them are the flight paths that the aircraft must take or are taking to their destination. So this is an example of transportation networks. And that's not all. In the city where I live, where I'm making this video from, what you see here is a part of the Google map representing the city transportation network. All of these are examples of transportation networks. So let's see another example of transportation network, which is road networks. So the example we see here is a show of some of the most complex road networks in the world. I took out this video from YouTube and you can see the link there. So what you are seeing here is an application of graph theoretic concepts in the design to optimize the traffic flow of the system before the physical structures are actually designed, and the optimization is evident after the design. Another example of networks is biological networks. So the figures you see here show 3 biological networks. The left, which is the green one on the left side, is the protein interaction network of yeast. The middle one is a neural network of roundworm, while the one on the far right, which is the blue one, is the food web species of the Florida Everglades. And this is also taken from the book of Filippo Mengsa. So, from the examples we have seen so far, what is the need for us to study graph theory? Graph theory answers some technical fundamental questions such as: how can we lay cables at a minimum cost to make every telephone reachable from the other? There are some parts of the world where they still use telephone cables. In fact, almost every part of the world. Recently, I saw one of the telecom companies laying fiber optic cables in my neighborhood. They were digging some parts of the street, putting cables, and then covering it up. So we can learn about how to lay those cables optimally by using the concepts of graph theory. What is the fastest route from the federal capital to each state capital in any country? What is the maximum flow per unit time from a source to sink in a network of pipes? This is very important when you consider a process system, a city water supply system, so on and so forth, or even the system in a building. You are constructing a building. This can help you to optimize the system design. How can n jobs be filled by n people with maximum utility? How many layers does a computer chip need so that wires in the same layer do not cross? If you have taken a look into the details of how computer chips are manufactured, you will understand that it can be optimized by using concepts of graph theory. Indeed, it has been used very well in that area. In what order should a traveling salesman visit cities to minimize travel time and maybe cost? Now, this is the application of graph theory to logistics. How can a season of sports league be scheduled in the minimum order of weeks? Of course, you can use concepts of graph theory for scheduling. How can we color the regions of a map using only 4 colors so that neighboring regions receive different colors? This is the area of graph coloring. We continue. Do birds protect crops by reducing insect populations? Now this sounds like a research question. which can be answered by using concepts of graph theory. So you see the immense opportunities that the knowledge of graph theory provides for you. How do we identify bottlenecks in a railway system? You can study the system using the concepts of graph theory and design an efficient solution to the problem. Like we saw in the previous video clips which I showed you, which I got from YouTube, and you will see that what they did was, before those complex structures were designed, there's the traffic condition on those parts, if there was, it should formally be a nightmare. So a more efficient design produces a more efficient structure that makes the traffic bottlenecks to be solved. Why exactly do all movie stars seem to be connected to Kevin Bacon? This is a research question again, which can be answered by the concept from graph theory. What do several Facebook users have in common? So we want to analyze. Analytics in social networks is something that can be done using concepts from graph theory, etc. We can't answer all the questions here. Now, there are some books in graph theory that are just on the applications of graph theory, engineering applications of graph theory, social science applications of graph theory, computer science applications of graph theory. So the topic is very wide. So what we are learning in this course is to get the foundational knowledge of the concepts of graph theory. You don't end there. From there, if you are interested, you can move on to any other application areas and you find it very useful. So let's look at networks and graphs. We can see something that is shown on the right hand side there. That's an example of a graph or a small network. We'll look at some definition. A network or graph, G equal to V, E, is a pair. That is V and E. They are a pair that consists of two finite sets having elements. V is a set and E is a set. 1. The set V equal to 1, 2 up to n is a set of points. They are called vertices or nodes. Either vertices or nodes can be used interchangeably. So if we come to the right hand side here, you can see an example of what we have. It's a graph. So this circle that you have 1, 2, 3, 4, 5, 6, 7, 8. They are all called vertices or nodes. And then there is also a set of edges. E can be described as a subset of I and J, such that I and J is in the set of vertices for all J not equal to I, of connecting lines called edges or links. So if you don't understand set theory very well at the moment, don't be bothered by this mathematical expression. So we are going to take a topic on set theory and all of this will become clearer. But let me try to explain it. So we say a set E, which is the set of edges, is a subset of Ij for Ij in V. So when we mean Ij here, we mean nodes, either node I or node J, such that node I or node J is in the set of vertices. Or we say vertex I, vertex J, such that vertex I and J is in the set of vertices where J is not equal to I, meaning that they are just different. See? So the I and J's here are the vertices 1, 2, 3, 4, 5, 6, 7, 8. In a graph, you can never have vertex 1 appearing twice. You can never have vertex 2 appearing twice. You can never have vertex 3 appearing twice. No vertex appears twice in the graph. That's what we mean by J not equal to I. They can never be equal. So what this means is a set of connecting lines that connect vertex I to vertex J, such that every vertices we are considering must be inside the graph. So this graph has only 8 vertices from 1 to 8. The set of edges must not be connecting to somewhere else, like 9 is not a part of a graph. Vertex 9 is not a part of this graph. So the edges must connect only vertices within this particular graph that we are considering. That's what we mean by this seemingly complex set theoretic statement that we have here. But we'll understand it better as we progress. So what is a graph? A graph is just a structure that contains vertices and some edges that are connecting the vertices together. Vertices are usually denoted either by using the letters U, V, or V1, V2, V3, Vn, or by numbers 1, 2, 3, 4 up to n, where n is the number of vertices. As you can see here, we simply designated them by using the numbers. Edges are usually denoted by the letters E1, E2 to EM, or we can also denote them by using this set. We have a parenthesis and then we have 1, 2. E1 equal to 1, 2 means that this is an edge, or there is an edge that is connecting vertex 1 and vertex 2. E6 means that E6 is an edge connecting vertex 5 and vertex 4. That's what we mean by this. So whichever way it can be represented. Now in the diagram I'm just using the two representations. You can also do that, even though it means a lot of writing. So we say E11, 8, 2. It's the same thing. You could have just said E11. But the 8, 2 actually tells you which vertices E11 is representing. So it is the edge that connects vertices 2 and 8 together. An edge can only connect 2 vertices. So when we say that one edge cannot connect more than 2 vertices, if there was a vertex between 8 and 2, then this edge no longer exists. Rather, there should be an edge here and there should be another edge here. Or it can be connected to a single vertex as a loop edge. So you can actually have an edge that goes like this. This is very straightforward. It's like you have a path that goes around and takes you back to the place where you started. We call that a loop edge. So an edge normally indicates a sort of relationship between 2 vertices it is connecting. Graph theory is so practical that you just see it everywhere. Imagine you are walking on a street. The street you are walking on are the edges. The buildings you are seeing on the street are the vertices. Suppose you are walking on the street. You are counting the trees. The trees you are seeing beside the street are the vertices, and the street or the path you are walking on are the edges. In a Facebook relationship or any kind of relationship is already a graph. Your family tree is already a graph. The items you have in your apartment, they are already graphs. Your colleagues and you already form a graph. Your work colleagues, your neighbors, everything is a graph. You see graph everywhere. So it is a very practical subject. However, graph theory is also one of the subjects that contains a lot of definitions. Of all the topics that I am aware of, I really don't know which topic has more definitions or as much definitions as graph theory. So please try to get used to it, where we'll do a lot of definitions in this part of the course. So we'll progress from here. What I'm going to show below is a part of a campus map. So I'll just show how it goes. Now this is the campus gate, the gate of the campus. So I'm going to call it DOU gate. And it connects to, just by the gate, there is a big building that is called the 1000 capacity hall. And then there is another building that is called the needs assessment building. And then there is an administrative building. And then there is a staff clubs after the administrative building. And then we have the faculty of computing. You can also move from the staff club to the security office. and you can move between the security office and the faculty of computing. You can also move from the security office to the admin building, from the same place to the workshop, from the workshop to the needs assessment building. From the workshop you can also go straight to the 1000 capacity hall. This is a map. We can be able to generate a corresponding graph from this map by using vertices and edges, which we can do by hand. And we can also write a Python program using NetworkX to generate it automatically. The vertices in this map are 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 landmarks on this map, as you can see. So the landmarks represent the vertices, and the paths that we can move to access these landmarks will be regarded as the edges. So if we transform this to a graph, we get something like this. You can see that the diagram on the right hand side, although it looks like the diagram on the left hand side, but it's like it has been flipped. It has been transformed laterally. Actually, when you transform maps or ideas or events or situations to graphs, the network or graph structure, physical structure, is not unique. It could be any structure. The nodes can be arranged in any way. However, the actual system is going to be the same. For instance, no matter where, what location in the xy coordinate that you put 2 or 8, there will always be an edge 11 connecting 2 and 8. So we see that the mathematical structure of the graph is the same. It's like isomerism in chemistry. The physical structure, the appearance may look different, but the chemical structure looks the same. So no matter how you arrange it, the mathematical structure of the graph is going to be the same. So we can start from 1 to 2 and call it E1, that is edge, the edge or the road link connecting 1 and 2. Then E2 is the road link connecting 2 and 3. E3 is the road link connecting 3 and 4. E4 is the road link connecting 4 and 5, so and so forth. So we get E5, E6, E7, E8, E9, E10, E11. So we have 11 roads connecting these landmarks together, and those 11 roads are the links or the edges, which is represented by using this set of edges. So a graph will always be described by the set of vertices and the set of edges. So we call this the equivalent network or graph. So a graph can either be directed or undirected. An undirected graph is a general graph in which the edges are bidirectional. Let's look at it this way. In the graph we saw before, the previous campus map, you can walk from anywhere to anywhere in any direction. When you can move from anywhere to anywhere in any direction, then we call that an undirected graph. This is the general graph in which the edges are bidirectional. So the order of the vertices does not matter. It doesn't matter how you order the vertices in that case. For example, the Facebook relationship, the campus map, etc. They are all examples of undirected graph. So we see an example here. You see the nodes or the vertices are connected by the edges in this graph. There is no arrow indicating which direction the edges are going. On the other hand, a directed graph, which we call digraph for abbreviation, is also a pair of edges and vertices. However, this is the graph in which each edge has a direction from its initial point to its terminal point. In this case, the order of the vertices matters. So we see an example. Email can be a directed graph. For instance, you may be allowed to send an email to someone, and or you may not be allowed to respond to an email depending on the situation. For instance, we get this often. So you get an email message from a particular organization and they say, please do not respond to this email, meaning that the traffic can come to you, but you cannot go back to the traffic. Another way to consider this is, supposing the campus map that we saw previously, you can walk in some of the paths or the roads, you can walk in only one direction. You can't go back in the same direction. So it's a one-way street. Consider one-way street where you can drive in a particular direction, but you cannot drive back on the same road. You have to go through another route if you are coming back to where you started from. So such kind of roads make a digraph. As you can see from this diagram here, when you have an edge that has an arrow going this way and an arrow coming this way, what it means is this is a bidirectional access way or bidirectional relationship, meaning that you could have represented it with two edges. One edge is going and another edge is coming. Now when you have an arrow going in one direction, that is a one-way direction or one-way relationship. Same as this one, same as this one, same as this one, same as this, same as this. This one is two-way relationship or asynchronous. I want to make a comment that whenever a graph is mentioned in any book or in any situation and digraph is not specifically mentioned, then you will assume that it is an undirected graph. Unless where a digraph is mentioned will you know it's a digraph, or unless when you see arrows in the diagram of a graph, that is when you know it's a digraph. So apart from general graphs and directed graphs, there is also something called a weighted graph. In this case, a weight is associated with the edges of the graph. So we have examples here. So a general graph which is not a digraph can be weighted, and a directed graph can also be weighted. So this is very practical. For example, roads come in different sizes. Some roads can take 2 vehicles at the same time. Some roads can take 4 vehicles at the same time. So we can use the weight or the size to indicate the size of the road. That's one example. Another example is a pipeline network. City sewage network, water pipeline networks. If you look at the network, if you go to a refinery for instance, you discover that all the pipes are not of the same size. In your flat for instance, all the pipes are not on the same size. The pipe that connects your water closet to the sewer is usually bigger than the one that is in your wash hand basin or in your kitchen sink. So that's another example of directed graphs. Email is also a weighted digraph, a weighted graph or digraph where email traffic indicates the weight. So the diagram you see here is giving you a cleaner picture of weighted, unweighted, directed, undirected. This is taken from the book of Filippo Mengsa. So we can see what we just described earlier on in a glance. So a graph can be directed or undirected, and whether a graph is directed or undirected, it can be weighted or unweighted. So on the top here we have unweighted, and then below we have the weighted graph. So let's go on to definitions. Like I said before, graph theory is one of the terminology intensive courses that you're ever going to learn. First of all, we start with something called the order. The order of a graph is the number of vertices, and is usually denoted by this V, absolute value of V. In the same way, we talk about the size of a graph, which is the number of edges in the graph, indicated by the absolute value of E. We talk about adjacency, the adjacency of two vertices. Two vertices are adjacent if they are directly connected by some edge. If there is a street or a path between you and your neighbor's house, then you are adjacent. In the idea of graph theory, then you are adjacent. Of course, the idea may be different in real life, you know. You may be adjacent to somebody in the neighborhood, but in graph theory, if you don't have access to the person, you cannot walk to the person's house in any way, then in graph theory you are not adjacent. Okay? So adjacency means there is a connection between you and another node. The node may be far away from you, the node may be close to you, you are adjacent. The neighbors of a vertex is the set of vertices adjacent to a particular vertex, and it's usually denoted by using this. So we say the neighbors, every Vj in V that is connected to Vi is a neighbor. It doesn't matter how far they are, how distant they are, as long as there is a connection between them, it's a neighbor. We describe a cluster. Any subset of vertices and edges in a graph form a cluster. Now, if you are not following these definitions, don't worry. In the next page, we are going to see an example in which we will practically calculate all of these parameters by using graphs, so it will become clearer. An edge is incidence with the vertices that it connects. So if a road connects house V to house J, we say that that particular road is incident with house V and house J. The degree is the number of edges incident with the vertex. So how we say the degree of valency of your house is the number of roads that leads to your house. That is the degree of valency. Now, when we talk about degree of valency, that deals with undirected graphs, general graphs. When we go to the digraphs, we start talking about two different kinds of degrees. We have the in degree. What is that? It is the number of edges incident into vertex V. So, how many roads can people pass to your house? That is the in degree of your house. We can also talk about the out degree. How many roads can people pass out of your house? Now, this only matters if there are some roads to your house that are only one direction. If every road to your house is bidirectional, you can come through and go in the same way, then we have an undirected graph situation, then we can only talk about the degree. But if there are some ways you can pass into a particular building and you are not supposed to go out in the same way, that's when we'll talk about the directed graph situation, and we can talk about the in degree and the out degree. And this is very practical. There are some buildings that the way you go in is not the same way you go out. You go out in a different way. So how many ways can you get in? That's the in degree of that building. And how many ways can you get out? That is the out degree of that building. When the number of ways to get into the building is equal to the number of ways to get out of the building, then we say it's a balanced graph. So if we have a graph of 10 buildings, a directed graph of 10 buildings, and we are calculating for this particular 10 buildings, how many ways can people go into them if we add all of them together? And how many ways can people get out of those buildings if we add all of them together? All the ways to get out, we sum them. All the ways to get in, we sum them. If the ways to get in to the 10 buildings are equal to the ways to get out of the 10 buildings, then we say that the graph is balanced. Otherwise, it is not balanced. And we see an example. So, let's look at two graphs here. One of them is a graph, general graph, undirected graph, and the second one is a digraph on the right side. The order of G. So we differentiate between them. So we generally use G for the undirected graph. We use G for the digraph. The order, which is the sum of the vertices, is 1, 2, 3. Both of them contain 8 vertices. The order of G is equal to the order of D, and both of them are 8. The size is the number of edges. So for the general graph, we have 1, 2, 3, 4, 5, 6, 7, 8 edges. But for the digraph, the size is different. Like I said before, when you have an arrow this way and another arrow this way, it's actually 2 edges. You can draw 2 edges. And we'll see other examples in some parts of this course where we actually draw the 2 edges. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's where we got this 10 from. So, talk about adjacency. So, in G and D, 1, 3, and 4, they are adjacent to 2. So, this is node 2. We said adjacency means there is a link between this particular node and several other nodes. there are only 3 nodes that connect to 2. So we say 1 is adjacent to 2, 3 is adjacent to 2, and 4 is adjacent to 2. If there was a node connecting 2 and 5, then we would have said 5 is adjacent to 2. So we now say the neighbors of 2 are 1, 3, and 4. It's the same thing for the digraph and for the undirected graph. It's not always going to be like this, but you just look at the diagram you're looking at and you draw out your conclusion based on what you're observing. So what are the neighbors of 5? Only 4 actually. So only 4 is adjacent to 5. What are the neighbors of 6? 7, 8, and 4 are adjacent to 6. Same way here. 7 has only one neighbor, and that is 6. When we say incidence, we are talking about the incidence of an edge. For instance, this edge is incident on node 1 and node 2. So we can say the degree of 6. For instance, the degree of 6. And when we talk about degree, we are talking about the undirected graph. When you talk about that graph, it's going to be in degree and out degree. So we say the degree of 6 is how many edges are incident with 6. We have one edge, the second edge, and the third edge. Therefore, the degree of 6 is 3. 3 edges are incident with 6. That's why the degree is 3. Can we guess the degree of 4? So 1, 2, 3, 4. The degree of 4 is, of course, 4 edges are incident with 4. The degree of 3 is 1, 2. 2 edges are incident with 3. And when we still look at incidence further for the diagrams, we talk about in degree and out degree. So we'll come to this side. What is the in degree of 3? Meaning how many edges are going into 3? How many roads can you use? How many ways can you enter building number 3? It's just 1. So the in degree of 3 is 1. And also the out degree of 3 is 1. What about the in degree of 4? We have 1 coming in and we have another one coming in. So the in degree of 4 is 2. What about the out degree? So we talk about the out degree of 6, for instance. Out degree of 6 is 1. Only one edge is coming out. Can we also talk about the out degree of 2? Of course, 2 is 1. What about the out degree of 4? 1, 2, 3. So the out degree of 4 is 3. Is the graph balanced? And when we want to talk about balance, we are not dealing with ordinary graphs. In fact, every ordinary graph is balanced because it is bidirectional. So the critical issue with balance is when you are dealing with diagrams. Is this graph balanced? What we can do, like I described before, is to count the number of ways to enter each of the nodes and the number of ways to come out. So I have a list here that lists all the 8 nodes in the diagram. And we are going to look at all the in degrees for each of the nodes one by one. The in degree of 1 is 1, the in degree of 2 is 2, the in degree of 3 is 1, the in degree of 4 is 2, the in degree of 5 is 1, the in degree of 6 is 2, the in degree of 7 is 0, the in degree of 8 is 1. So the out degree of 1 is 1, the out degree of 2 is 2, the out degree of 3 is 1, the out degree of 4 is 3, the out degree of 5 is 1 again, the out degree of 6 is 1 again, the out degree of 7 is 1, and the out degree of 8 is 0. So when we add them together, we have 10 here, we have 10 now. You should do this calculation yourself to be sure that everything is correct as I put it here, because sometimes I'm in a hurry. If it is not correct, drop a comment so that I can correct it in the next note. So what do we conclude? The diagram D is balanced because the total number of ways of going into the nodes is equal to the total number of ways of coming out of the nodes. So we are still looking at definitions. the null graph. It is the graph that has no edges, no vertices. A graph that does not exist. A building that does not exist. And then we talk about the vertex graph, which is indicated by this green here. It's an edgeless graph having only one vertex. Consider a building, a single lone building in a wilderness without any access. That's what a vertex graph looks like. Then we talk about the loop graph. It's a single loop with its one vertex. So we have this loop edge that is coming around and getting back to the vertex that I started from. This is a loop. If this is the only graph, the blue one here, then it is a loop graph. Then we talk about a link graph, which is a single edge that connects two vertices. So if we take 1, 4 and this yellow link connecting them, we call it a link graph. And then we talk about parallel edges. Two or more edges that join the same pair of distinct vertices. So you can have a road, a bidirectional road linking a building, and then you can also have another bidirectional road in another direction, another area linking a building. So it's like they are parallel. That's why we call them parallel edges. Now if we go further to define a simple graph, it is a graph or a diagram that contains no loops and no parallel edges. When a graph does not contain any loop, doesn't contain any parallel edges, we call it a simple graph. And then we describe an arc. An arc is a graph or diagram with n edges and n plus 1 vertices. So the edges are one less than the vertices. We are going to see an example in the next page, so don't worry about the theory now. And then we describe an n circuit. It is a graph or diagram with n vertices and an equal number of edges. We call it a circuit. A complete graph is a simple undirected graph that has the maximum possible number of edges, and usually denoted by using k to the subscript of n. First example is we have just this simple graph, single node in a wilderness, no connection. And then we have this link graph here. These two examples already are complete graphs, the maximum number of edges. For example, because this is one node, what's the need of an edge? There is no other node to connect to, so no need for an edge. So this one is, you already have one edge connecting the two vertices. That is all. As long as it is bidirectional, you can go through this way. You really don't need any other route. So it is a complete graph. What you see here is also a complete graph. So what you see here is already an n circuit. N circuit because we have 3 nodes and 3 vertices. That's what we described before. So we have 1, 2, 3, 4, and then we have 1, 2, 3, 4, 5, 6. This is a complete graph. The maximum number of connections is right here already. You can move from every node to every other node directly without passing through another node. And we have this complete graph also. 1, 2, 3, 4, 5. You can move from every node to every other node without passing through another node. So these are the complete graphs for 1 to 5. 1, 2, 3, 4, 5. So this one now will be denoted as K, 5. This one is K, 4. So when you are asked to draw the K4 graph, you know exactly what to do. You just draw the 4 nodes and make sure that every node is connected to every other node. K3 graph, K2 graph, K1. By now I believe you already know how to draw a graph by hand if we give you a map or we give you a situation. But let's see how to use computer to help us to do the job. So we are introducing NetworkX. Small graphs or simple networks are easy to be drawn and managed by hand. However, when the graphs become complicated, like we saw the Facebook network, it's not possible for you to draw that with your hand. So several tools are available to draw and manage graphs. Among them is NetworkX. You can visit the web page of NetworkX at networkx.org. NetworkX is a Python package for the creation, manipulation, and study of the structure, dynamics, and functions of complex networks. To use NetworkX, you have to install it inside Python using pipe install. We see how to do that as we progress. And you should also install some other required libraries such as NumPy if you've not already done that, Matplotlib if you've not already done that. Make sure you have a good internet connection. You are encouraged to download the documentations from the listed websites, and you see the user manuals on how to do these things. Now, if you are not familiar with Python, you can visit my Python tutorials that covers all the basics of Python that you need to be able to follow this part of the course to do the installation on your system. So, let's see how to install NetworkX in Visual Studio Code. So if you have already set up Visual Studio Code on your system, if you don't have NumPy installed already, just do pipe install NumPy, pipe install Matplotlib, and then pipe install NetworkX. The reason is because NumPy package is required for arranging the data, graph data, in such a way that you can be able to plot it. Matplotlib is actually the package that helps you to plot the graphs and show them in a window. And NetworkX contains all the libraries that you need to manipulate graphs and networks. So, if you don't know how to set up Python with Visual Studio Code, you can visit this YouTube link here, which gives you a description on how to do that. Now we are going to go to Visual Studio Code and try to perform these installations. So here we are in Visual Studio Code terminal. Make sure you have an internet connectivity so that you can be able to do the installation. Okay, so you just say pipe install NumPy. Requirement already satisfied because I have installed NumPy before. But if you have not, it's going to start downloading the packages and start installing them. When you see the prompt back shown on the screen, it will tell you it has successfully installed it. Then you can continue and say pipe So I have already done that before, so it doesn't need to do it again. Then you can now say pipe install NetworkX. Requirement already satisfied. After you have done that, you are ready to begin using NetworkX. So continue with the So let's see how to create graphs in NetworkX. You can create graphs either from the Python command prompt or by writing code. We are going to go the way of writing code here so that we can actually store the codes in a file and be able to access it later on. We call this NetworkX 0.py. This program introduces NetworkX. First of all, we'll clear the Python console as usual for the purpose of having a clean console when we are running programs. Main program begins here. We have to import NetworkX into our Python workspace. So this is a popular alias. Import NetworkX as NX. We also need to import matplotlib.pyplot using an alias. PLT is also a popular alias. This is for plotting the graph, showing the graph actually in the graph window. Now we'll create a new graph. So we can just call it G equal to nx.graph. This dot graph is what actually creates a graph. Dot graph creates an ordinary undirected graph. This is not a digraph. So you can add a node to the graph immediately you've created it. So we use this add node function to add the node. So we give the node a name, node 1. We can also add another node, call it node 2. It's a very simple graph. And then we can create an edge. We use the add edge method or function. So when you say edge 1, 2, it's just like the way we did it when we are writing it in the note. Means that there is a connection between node 1 and node 2. That's how we've created the graph. Now we want to show the graph by plotting it. So you now use plt.figure. You can set the size of the figure. For instance, the window size is 2.5 by 2.5, which will be square. That's where we are going to plot it on. That's not all. And then you draw the graph. You now say nx.draw NetworkX. This draw NetworkX is actually what draws the graph in the window. And what graph do you want to draw? The G which we created. So you put it inside it. That's not all. You need to show the plot. You now say plt.show. Now before I run this program, there is another way to do it easily, in which as you are typing the code, you just see the graph being plotted in a web page, and that is by using Jupyter Notebook. So that may be an option for you, which is a very good option. But in this class, I want us to be able to create several graphs at once and show all of them in separate windows at the same time on the screen. So that's why I'm using this approach. If you run the program, this is the output you get. It just plots the graph of 2 nodes and 1 edge connecting them. This will not always be the arrangement. If you plot it several times, 2 may be on the left hand side and 1 may be on the right hand side, 2 may be at the bottom and 1 at the top. It's not unique. The physical structure is not unique, but the mathematical structure remains the same. Node 1 and 2 and an edge connecting them. So here we are back in Visual Studio Code. So we open the folder where the files are kept, and this is our first file which we just described now. And you can just click run. Okay, so it took a pretty time for our graph to show on the screen, but here is the graph that we just shown. You see, you can see, like what I described before, that the plotting of the graph is not unique. You can see the one in the book and you can see the one that was actually plotted for us. So the arrangement, physical arrangement, every time you plot it may not be the same, but the mathematical structure of the graph remains the same. Now let's see another example of creating graphs in NetworkX. We'll call this NetworkX one. We are going to create something a little bit more complex than the one we did before. So as usual, we import NetworkX and we import Matplotlib. So this time around we have G again equal to graph, and we created the node 1, 2. This is the previous program we did. Let's expand on it. We want to add several more nodes at once. If you keep adding all the nodes one by one, that's a tedious process, like manual labor. So suppose I want to add 1, 2, 3, 4 nodes immediately at once. So we can just create a list and put the list into the add nodes. This time around we say add nodes from 3, 4, 5, 6. So we now have 1, 2, 3, 4, 5, 6 nodes in the graph. And we can also add edges from a lot of edges at one time. Nodes 3 and 1 are connected by an edge, 3 and 4, 4 and 5, 5 and 6, 1 and 6, 2 and 3. So we can print a message. We want to see the nodes and vertices of the graph. We are now using NetworkX to perform some operations for us. If we say print g.nodes, it's going to print all the nodes in the graph, and that is 1, 2, 3, 4, 5, 6. We also want to see the edges of the graph. If we say print g.edges, it's going to show all the edges in the graph. Now we can plot the figure. Set the size to 4.5 because this is going to be pretty bigger than the one we did before. Draw. First of all, you create the figure, then you draw the graph, and that's not all, you must show the plot. When you show the plot, that is when it comes on the screen. Now when you run this program, this is what you get. So you see the physical appearance is not unique. We are going to run the program now and see that what it shows us may be different from what we see here, but the mathematical structure remains the same. Now the output here shows when you printed the vertices or the nodes, you have 1, 2, 3, 4, 5, 6. And when you printed the edges, this is what you have. 1, 2, 3, 4, 5, 6, 7 edges. 1, 2, 3, 4, 5, 6, 7 edges. So let's go to Visual Studio Code. This is the program we just described. And we are going to run the program now. Okay. So you can see that the physical appearance of the graph plotted here is different from the one in the notes. In fact, this one looks better than the one in the notes. If you plot it again, it's going to give you something different. Okay. So, but the important thing is we have our graph here, and then we have our nodes listed here, and then we have our edges. You can check out the edges to see that it corresponds with what we have. For instance, this is 5, 4. They are connected. 4 and 5. This is 4, 6. They are connected. That's 4 and 6. This is 3 and 4. They are connected. That's 3 and 4. Now let's see how to create diagrams in NetworkX. We'll call this program NetworkX2.py. Introduces NetworkX diagrams. The same way we import NetworkX, and we also import Matplotlib. Now we are going to say d equal to nx.diagraph. This creates a new diagram. We can also add nodes. Add nodes from 1, 2, 3, 4, 5, 6. And then we can add edges, connecting lines. Add edges from. Now let's show the number of vertices or the number of nodes. D dot number of nodes. The number of edges. D dot number of edges. Take note, this is number of nodes. It's going to give us a particular number. It's not d.nodes. D.nodes will list out the nodes. D.number of edges is going to give us the number of edges and not the edges. D.edges will list out the edges. So create the figure, draw the graph, and show the plot. Now when we run the program, you see number of vertices 6, number of edges 9. If you plot the graph, this is what it looks like. You can see the arrows that indicate the direction. In fact, you can confirm that by looking at what you have in the plot. So we'll go to Visual Studio Code and see how it runs. So here we are in Visual Studio Code. This is the program that we just described. Let's run it. Number of vertices 6, number of edges 9. So if you expand this out, you can see what we have here. Okay. Okay, so before we round up the class today, we are going to have our first homework or lab 1. Now, if you recall the campus map of page 19 in this slide, we have this map structure, and we actually drew the graph by hand. Now I want you to write a program using NetworkX to draw the graph of the campus map, this exact campus map, using the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's see how it looks like. The second lab you are going to do is create a friendship graph of you and 9 other people you know. There could be flatmates, there could be neighbors, etc. Just create a friendship. You will be node 1, and the other 9 people will be nodes 2 to 10. Now, if any 2 of you are friends, create a link between both. Try to draw the diagram using pencil and paper to begin with, and then write the program using NetworkX to draw the diagram and show the plot. Indicate whether this is a graph or a digraph. Can it be a graph only? Can it be a digraph? Or can it be both a graph or a digraph? Textbooks remain the book of Balakrishnan, Edward Platt, and Filippo Mensah. Other materials, YouTube video tutorials. Be sure to check out my video tutorials and other numerous online tutorials. So we have come to the end of the first class of a series. Please like, share, comment, and subscribe for more videos. Thank you, and see you in the next class.